Let's talk about the hydrogen bonds and specifically how the strength of hydrogen bonds affects its boiling temperature. So if we take a look at this graph, we can see a couple of things. We want to compare hydrogen bonds between different molecules and how that boiling point is going to be playing a role depending on what's attached to that. So as you can see from here, it seems to me that water has a boiling temperature of about 100 degrees Celsius. And if I take a look and I change the oxygen to something like a sulfur, you can see that instead of being H2O, it actually ends up having H2S. And because it has this H2S, something really interesting happens here. The boiling point drops for water from an H2O to an H2S. And here is where it gets a little bit more interesting, because if you change this to an HSE, the boiling point begins to rise. However, if I move, instead of being an oxygen, I go to a nitrogen, and I go down this way, the boiling point begins to drop. And then if you take a CH4 and an SiH4 and so on, in group 4, you can also see that relative to these three lines, you're going to end up having a hydrogen that is definitely attracted to something less electronegative. So the question is, why is it that these hydrogen bonds can affect the boiling point to such a high degree? And so let's go ahead and investigate that a little further. When we're talking about polarity and strength of intermolecular forces, what we're really talking about is the potential energy of the electrons. They're associated with the negative pole of a molecule, and they're going to decrease as they approach the positive pole of another molecule. So if I take a high potential energy, for example, if I move them far apart and I ask you what is the potential energy for here, you can kind of see that these molecules are extremely large, which means that if I put them closer together, they're going to have a lower potential energy, meaning that if they have a much closer distance, they're going to able to have that energy realized. And so it's kind of weird, because normally you would think that the closer they are, they would have a higher potential energy, but the reality is that because they're so close, they've already turned that into a Coulombic force. So again, thinking of strength, it's always going to have to do with that distance. Molecules with stronger dipoles will have stronger attractions for one another, which eventually pull them close together. This is going to increase the potential energy as the molecules are going to move closer. So in order to do that, energy must be added in to weaken or to break those forces. So every single time you want to break an IMF force, you have to be able to provide some energy. And then the potential increases as the molecules begin to move away. So let's take a look at this example here. Let's put a polar molecule like water, and let's add something non-polar, like for example a hydrocarbon. We're going to put them next to each other, and there is going to be some sort of induced dipole. So what happens here is the polar molecule is actually going to rearrange the non-polar a little bit to move that negative charge this way. When it does that, it actually turns the non-polar species into a polarized molecule. And so by doing that, you're going to see a negative, a positive, negative, and a positive. And so now that non-polar species has had what they call an induced dipole. This is very similar to what you see when you have ethanol. Generally, it's an alcohol that has a polar region and a non-polar region, but it will reorient itself so that it attaches itself to the polar side. So the attractions resulting from that dipole-induced dipole are stronger when the magnitude of the dipole in the molecule is large. So if I have a very strong dipole moment in the polar area, you're going to induce a much larger dipole in the nonpolar. So in just generally speaking, in a more of a concise fashion, the strength of the dipole-induced dipole also increases when the nonpolar molecule has a larger electron cloud and is more polarizable. So this part right here, make sure you understand this about this idea of polarizability. So certain molecules can actually get polarized. Alright, and that brings us to our next dipole, which is called dipole-induced dipole, aka London dispersion forces. So these exist between every single atom, nonpolar, polar, ions, atoms. So if you ever are in doubt in terms of what IMF to use, always include some sort of induced dipole. And what they usually do is they will include contributions of force between all particles. The London dispersion forces are the only intermolecular forces that can keep the nonpolar species together. So if I ask you right now is, what is a region of a nonpolar? If there is some sort of force that holds them together, it's going to be a London dispersion. These are actually caused by Coulombic interactions, and usually from this idea called the induced dipoles, which means that if you have a highly polar region and a nonpolar area, you're going to be able to create that induced London dispersion force, aka induced dipole. So I really want you guys to really consider this idea that London dispersion forces are it's really what happens when you get a dipole and it induces some sort of polarity on a nonpolar molecule. So kind of really complex stuff, but basically that's what a dispersion force is, and generally it will occur even on nonpolar molecules. Alright, so here's the example of that. So if I take a negative charge in time and I give it a 0.1 seconds, the instantaneous charge on this is going to rotate. So the negative charge is going to continuously rotate because of the electron cloud, and you're going to get this induced dipole. At 0.2 seconds, you can see that you can also get that negative charge moving around 12 o'clock, at 0.3 seconds, 0.4, and so on. And ideally, over time, this molecule is becoming nonpolar, even though it has polar and negative charges, because it kind of almost balances out. But there is an instantaneous polarity at any 1 second. So if I pick any spot in here, you get an instant dipole. But overall, it's called a London dispersion force. Alright, so here's what happens on a London dispersion force, aka induced dipole. At 0.1 seconds, you can see that you have a positive 1, positive 1, positive 1 charges. At 0.3, this dials up to a negative charge, and so on. As you can see, these are the dipoles that you have, or what they call the instantaneous dipole. It's almost kind of like a clock. If I were to pick a time here, at 3 o'clock as an example, you get a dipole. Here at 9 o'clock, you get a dipole. And so species with more electrons and larger electrons are more polarizable. So it just generally makes a lot more sense, right? The more electrons you have, the more they're running around the cloud. Because they're moving around the cloud, they're going to end up having more of this dipole moment. So if I compare helium versus something like iodine as an example, iodine is a fairly larger molecule relative to helium. Remember, it's the halogens, right? And so if you take a look at the molar mass, it's 240 grams per mole, and the boiling point rises to 460, which means that because it has such a larger electron cloud, it's going to be more polarizable, and because it's more polarizable, it's going to have stronger forces, and because of that, it's going to have a higher boiling point relative to bromine, chlorine, and fluorine. So the question here is, why is that the case? And the reason why is because they have a weaker hold on those outer electrons, as those electrons are moving on the outside. So as I'm moving down a group, it creates atoms with more electrons. And the more electrons it has, the more polarizable it becomes. And that's not always true when we're going left across, because atomic radius would increase, and therefore the size of the cloud increases. So across a group, it's a little bit of a different story, but up and down, it's a lot more clear. Now, let's talk about shapes real quick and how these shapes play a role in dispersion forces and physical states. So if I look at this picture real quick, you can kind of see that this is a hydrocarbon. And the hydrocarbon is built around this idea of carboxyl group, the CO. You also have CHs across, and you can automatically say wait a minute, is this a polar or is this a nonpolar molecule? And as you can see from here, obviously this is considered to be a nonpolar region. But there is a polar region here on the CNO. Now, if I go ahead and change that, that's actually saturated fat, by the way. Saturated meaning that you have to be putting a bunch of hydrogens all over. However, in unsaturated fat, you have some bent structures in here. So if I ask you, which is the stronger ones, which one has a little bit more, which one can you dissolve a little better, etc., you can kind of make the case that here we're missing those hydrogens. And the question is, how does that play a role in its strength? And so generally speaking, as the dispersion forces increases, the contact area between the molecule increases. So in this specific case, what you're having is stronger dispersion forces because the CH3s have polar and nonpolar regions. They're being attracted. However, these more of our weaker ones. So the reason why is because this chain's a lot longer, it's going to have larger dispersion forces, which means that it has higher contact area. Here you have weaker dispersion forces, meaning that they're also going to have weaker strengths. Okay, we're going to do part 3 here in a bit, so stay tuned.